into Banach space. Meeting is being live stream recorded. Stream is not you cannot consent being live stream anyone to access. So can we share it? Got it. So Banach space. Share. So whiteboard. So Banach space. So linear transformation. No, we need to discuss what is the linear transformations. Linear transformations. No? So the transformation T. The transformation T is transformed from one normal linear spaces to another normal linear space. Another normal linear space. Another normal linear space. This space. So that is n to n dash. So T is a transformation. It is a transformation. So we say it is a linear. So satisfies the following conditions. What are the satisfied following conditions? First condition. T of x. T of x. Yep. Share. So T of x. So condition number 1. T of x. X plus T of x plus y. T of x plus y. T of x plus y equal to T of x plus y equal to T of x plus T of y. T of y. So for all x comma y belongs to n. So second property. What is the second property? Second property is T of alpha of x that equal to alpha into T of x. So what is this alpha here? Alpha is a scalar. It's a scalar. So third property. What is third property? Nothing but combining first property and second property. First and second property means what is the first property here? T of alpha x plus beta y. It can be written as alpha into T of x plus beta into T of y. T of. So here what is the alpha? Here alpha comma beta are scalars. This is scalars. So x comma y belongs to n. So what is the fourth property? So what is the fourth property? Yeah, fourth property is suppose T is a fourth property is T is continuous. Continuous. Normal linears. Continuous. Continuous. Continuous in normal linear space for sequence xn. Sequence xn. Then so xn tends to x. That implies T of xn tends to T of x. So using these four properties, we need to prove the theorem. What is that theorem? Let T be a theorem number 2. Theorem 2.3.1. theorem 2.3.1. Theorem 2.3.1. What is that? Let T be a linear transformation. Let T be a linear transformation. Linear transformation. Linear transformation from normal linear space N. From normal linear space. Normal linear space N. N into normal linear space into normal linear space. Normal linear space N dash. The following properties are equivalent. The following properties are equivalent. Equivalent. What is the property? First one is T is continuous on N. T is continuous on N. Second one is, what is second one? T is continuous at the origin in N. T is continuous on origin N. So clear one. Next, what is the third one? Third one is, there exists a real number. There exists a real number. There exists a real number. M is greater than or equal to 0. Such that so norm T of X less than or equal to M. Norm X, norm of X, for all X belongs to N. For all X belongs to N. So fourth one. What is the fourth one? T is bounded on closed unit sphere N. T is bounded on closed unit sphere. Unit sphere of N. That is, TS is bounded subset of, that is, T of S is bounded subset of N dash. Bounded subset of N dash. So, okay, next. Proof. This is obvious. First one. What is this? 1 implies 2. Implies 2. This is obvious. This is obvious. So since T is continuous, since T is continuous, at each point of space N, each point of space N, Hence, particularly at the origin. Hence, particularly at the origin. At the origin. Right? Particularly at the origin. So 2 implies, so 1 implies 2 we did. Next one, 2 implies 2 implies 2 implies 1. 2 implies. Assume that T is continuous at the origin. Assume that T is continuous. T is continuous at each point of T is continuous at the origin. At the origin. The origin. And we shall now show that T is continuous. T is continuous. Each point. So each point of X in N. What is N? N is a normal linear space. And dash is the another normal linear space. So for the sequence Xn, with the condition for the sequence Xn, for the condition previously discussed before linear transformation condition number 4th condition we are using here. What is that? Sequence for the condition for the sequence. So Xn tends to X. That implies T of Xn. T of Xn tends to T of X. T of Xn tends to T of X. So Xn, T of Xn tends to N. This condition is in N. This Xn tends to X in N. N means normal linear space. That implies T of Xn tends to T of X. This is another normal linear space. That is, what is that? That is N dash. So in the statement only, we took N is the one normal linear spaces, N dash is the another normal linear space. Okay, next. So since T is linear, so we have to clear this one. Since T is linear, we have T of Xn. We have T of Xn tends to T of X. That equal to what we are doing here. T of Xn tends to T of X. So transpose T of X, RHS to LHS. What you will get? T of Xn minus T of X. That equal to 0. That means in this one, what we are doing, in these two, you have to take it, T is capital T, you take it outside common. Yeah, T of Xn minus X, that equal to 0. That equal to 0. That equal to 0. So that means what you are observing, T of Xn tends to T of X as N tends to infinity. Right? So that means 2 implies, that is 2 implies that means here 2 implies 3. 2 implies 3. So assume that 3 does not hold. Assume that 3 does not hold. Does not hold. So that is there no positive real constant. That is there. That is there is no positive real constant. No positive real constant. No real constant. Capital M such that. Norm of T of X. Norm of T of X is less than or equal to capital M. Norm of X. So norm of X for all X in N. For all X in N. X in N. So then for each positive integer. Then for each positive integer. Each positive integer. N. We can find Xn. We can find Xn. We can find Xn in N such that so we have to clear the code such that so norm of here norm of T of X. Norm of T of X less than or equal to capital M. Norm of X. X for all X in N. For all X in capital N. Norm of capital N. Select text spot trace. Okay. So for each positive integer, we can for each positive integer, each positive integer, then we can find an Xn in N, Xn in capital N, such that so norm of T of Xn, norm of T of Xn greater than N, norm of Xn. So that is so norm of T of Xn whole divided by N, norm of Xn. That equal to norm of is which is greater than 1. So let here Xn, that implies Xn whole divided by N into norm of Xn. So that it follows Yn tends to 0. It follows Yn tends to 0. So but here norm of T of Yn which is greater than 1 for every N or for all N can write. Now clear the code. So hence Hence, limit n tends to infinity. Limit n tends to infinity. T of yn that equal to 0. This is a contradiction to our hypothesis. This is contradiction to our hypothesis. Contradiction to our hypothesis. T is continuous at the origin. Then T is continuous at the origin. T is continuous at the origin. That means what we need to 3 implies 2. So let us assume that there exists a. Let us assume that there exists a. Assume that exists a positive real number. Positive real number. How positive real number? Capital M such that. So norm of P of x less than or equal to capital M, norm of x. For all x in n. So let xn tends to 0 in n. We show that T is continuous at the origin. We show that T is continuous. CTS means here CTS continuous at the origin. Yeah, now clear the board. Here continuous at the origin. That is xn tends to 0 in n. That implies T of xn tends to 0 in n dash. Here n and n dash we are writing. What is n? N is a normal linear space. N dash is the another normal linear space. Here xn tends to 0 in n, and that implies T of xn tends to 0 in n dash. And n dash. Next. So now norm of T of xn minus 0 that equal to norm of T of xn minus 0 is less than or equal to capital M. And the norm of xn minus 0 tends to 0. So norm of T of xn minus 0 tends to 0. That means T of xn tends to 0. So in n. So 3 implies, that means 3 implies 4. 3 implies 4. So assume that there exists a positive integer. Assume that there exists a positive integer. maybe it's a positive integer, and a positive real number, and positive real number, positive real number, m such that positive real number, m such that, so positive real number m such that, m such that positive real number m such that, so P of n less than or equal to capital M of norm of x for all x in n. So we have to show that TS is bounded in n dash. What we need to do now, we have to show that P of s is bounded. P of s is bounded. P of s is bounded in n dash. P of s is bounded in n dash. We have, so norm of P of x less than or equal to capital M, norm of x for all x in n. Yes, in particular P of x. So first we need to clear the board. In particular, P of x less than or equal to m norm of x for all x in n. N, what is n? N is the normal linear space. So then P of x norm P of x less than or equal to m. Since here norm of x is less than or equal to 1, thus T of s is bounded. T of s is bounded. So 4 implies, next we need to do 4 implies 3. 4 implies 3. Right? So by assumption, by hypothesis, TS is bounded. TS is bounded. There exists M. There exists capital M. So a positive real number such that a positive real number such that positive real number such that norm of T of x less than or equal to capital M for all x in S. For all x in S. So if x equal to 0, P of x equal to 0, P of x equal to 0. So norm of T of x equal to 0 less than or equal to capital M into norm of x. So clear the board. So let x be a let X be a non-zero element in N. Okay, non-zero element in N. Non-zero element in N. Then non-zero element in N. Then X by norm of X. X divided by norm of X. X divided by norm of X. X divided by norm of X. So X divided by norm of X is in S. From above inequality we have. From above inequality we have norm of T of X divided by norm of X less than or equal to capital M for all X belongs to capital M. So norm of T of X less than or equal to capital M, norm of X for all X belongs to capital M. So thus this completes the proof. This completes the proof of the theorem. Proof of equivalent. Proof of theorem. So next what we have a Hahn-Banach's theorem. Hahn-Banach's theorems of three theorems are there. What is Hahn-Banach's theorem for real linear space? One, Hahn-Banach's theorem for complex linear space. Hahn-Banach's theorem for normal linear space. No? So here Hahn-Banach is a German mathematician. Banach is a Polish mathematician. So we are discussing about the theorem. First one is Hahn-Banach's theorem. That is 2.4.1. Hahn-Banach's theorem. Hahn-Banach's theorem. 2.4.1. No? Hahn-Banach. B-A-N-S. Hahn-Banach theorem. Theorems. No? In real linear space. We are discussing in real linear spaces. In linear spaces. So linear spaces. Statement 1. If P of X be a sublinear functional, if P of X be a sublinear functional on a real linear space N. Real linear space N and M and M and M. A linear space N and F naught. A linear space N and F naught means F suffix 0. A real valued linear functional. A real valued linear functional. Linear valued functional defined on M. Defined on M. Defined on M. Let F not satisfy. Let F not satisfy. F not satisfy. So F not X less than or equal to P of X on M, on capital M. Then there exists a real valued linear functional. Then there exists a real valued functional. Real valued functional. Real valued functional. F dash on N, capital N, such that F dash is an extension. F dash is an extension. Extension of F naught. Extension of F naught and F dash X. F dash X less than or equal to P of X on N. What is the statement? So once again, I am explaining main important. This is a 2.4.1 theorem on Banach's theorem. So on Banach's theorem for in real linear spaces. He proved three theorems in real linear spaces and complex linear spaces and normal linear spaces. First, we are discussing about 2.4.1 on Banach's theorem. If P of X is a sublinear functional on linear space N and M, a linear space N and F naught a real valued linear functional defined on M. Let F naught satisfy. F naught X is less than or equal to P of X on M. Then there exists a real valued functional F dash on N such that F dash is an extension F naught and F dash X is less than or equal to P of X on N. So we have to clear the board first. Next, proof of this theorem. Most important theorem, this is proof. So let M dash equal to M plus X naught, the square bracket. So where X naught belongs to capital M, where X naught belongs to capital M. Capital M. That is, M dash is a linear subspace. Then M dash is a linear subspace. Spanned by M. Spanned by M. Spanned by M. Spanned by M. And the element X naught. The element X naught. So every element M dash has the following unique representation. Then every element of M dash has the following unique representation. That means X equal to x equal to m plus alpha x naught. So alpha is real. Alpha is real. Real means nothing but scalar. So small m belongs to capital M. Define f on m dash as follows. Define f on m dash as follows. For any reals, f of m plus alpha x naught, that equal to f naught m plus alpha c. Then it follows f is a linear, m dash and is the extension of f naught to m dash. F is a linear and m dash. F is a linear on m dash and it is extension of extension of f naught to m dash. So we have to prove that f of x is less than or equal to, but we have to prove that f of x less than or equal to p of x. So we clear the board. X. Here x belongs to m dash. X belongs to m dash. So C must be chosen. So chosen that such a way f of m plus alpha x naught. F of m plus alpha x naught. That equal to f of f naught m plus alpha c. So less than or equal to p of m plus alpha n naught, m plus alpha x naught. So this is equivalent to the following conditions. This is equivalent to the following conditions. Equivalent to the following conditions. Equivalent to the following condition. What is that conditions? F of m divided by alpha plus c less than or equal to p x naught plus m by alpha for alpha greater than 0. Alpha greater than 0. So another condition, just we are replacing alpha by minus alpha of m divided by minus alpha minus c less than or equal to 3 into x naught minus m divided by minus alpha for alpha greater than 0. Right? Alpha. So before one is alpha greater than 0. Next we replace alpha by minus alpha. Minus negative value is always less than 0. So clear the code. So M is a linear subspace. Here M is a linear subspace. subspace. M is a linear subspace. M is a linear subspace. M divided by alpha, comma, M divided by minus alpha. Alpha belongs to capital M. Right? So we have f of f naught m minus p of m dash minus x naught less than or equal to c less than or equal to p of x naught plus m double dash minus f naught m double dash for all m dash comma m double dash belongs to capital M. Capital M. So observe that for any two vectors m dash in M, we have so m dash and m double dash in M. We have f of m f naught m dash plus f naught m double dash equal to f naught m dash plus m double dash less than or equal to p m dash plus m double dash. So here what we will do means in this case p of m dash plus m dash, we are minus x naught adding and subtracting for adjustment purpose. P of m dash minus x naught plus x naught plus m double dash. Yeah, that is less than or equal to p of m dash minus x naught plus, because minus x naught we added and x naught subtracted. So now we are separating. How we are separating? P of m dash minus x naught plus p of x naught plus m double dash. So now for any choice of C between the two real numbers. C is between the two real numbers. Between the two real numbers. So supremum, we have to first clear the board. Now supremum of m dash, small m dash belongs to capital M. Capital M that equal to f naught m dash minus p of m dash minus x naught. So what is the supremum? Supremum and infimum. So infimum of m double dash belongs to capital M. So here p of x naught plus m double dash minus f naught m double dash. So we get the property. We get the property. We get the property f of x is less than or equal to p of x for all x belongs to m dash. So now consider C is a family of all linear extensions G of f naught. G of F naught. Now for which the inequality, right, is the inequality. Is the inequality. What is that? That inequality, G of X is less than or equal to P of X. So holds in the domain of G. Holds in the domain of G. Holds in the domain of G. We now make set C is partial order. We now make set C partial order. Partial order. Partial order. Partial order. Ordered set. Set. Partial order. We clear the code. Partial order set. So with the following relations here, with the following relation, with the following relations, following relations. So G1 less than or equal to G2. G2 means the domain of G1 means the domain of G1. Domain of G1 is contained in the domain of G2. Domain of G1 is contained in domain of G2. Domain of G2. That means G1 of X equal to G2 of X, no? For all X in the domain of G1. For all X in the domain of G1. The domain of G1. So it is easy to see that union of any chain of extensions is also an extension. Therefore, there are upper bound of the chain. 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 By Jones lemma. By Jones lemma. By Jones lemma. So there exists a maximal element. What is that? Jones lemma. So upper bound of the chain by Jones lemma exists a maximal element. Exists a maximal element. Maximal element. So we denote the by F dash maximal element. We by F dash. F dash. You show that the domain of F dash. We show that the domain of F dash. So is the whole space of N. Is the whole space. Whole space of N. Whole space of N. Let M double dash be the domain of F double dash. Let M dash be the domain of f dash. Suppose m star belongs to n. So we have to clear the board first of all. So here m dash m star is not equal to n. Then there exists an element x belongs to n. Then there exists element x belongs to n. Such that x does not belongs to m star. X belongs to n such that x does not belongs to m star. What we observe? So m star is not equal to n. Then there exists a element x belongs to n such that x star does not belongs to m star. X does not belongs to m star. So consider subspace m double dash. Consider subspace m star m double dash. So m double dash equal to m star plus in the square bracket, nothing but square bracket, greatest integer function, x star. By our construction, there exists that by our construction, there exists a linear extension. Linear extension. F double dash of f dash from m star to m double dash. M star to m double dash such that f double dash of x is less than or equal to p of x, such that f double dash of x less than or equal to p of x for x belongs to double dash x, or x belongs to m double dash. So m double dash. Hence the domain of f dash is the domain of f dash is the whole space n. F dash is whole space n. Double H-O-N, whole space n. This completes the proof of the theorem. This completes the Proof of the theorem. Proof of the theorem. Yeah. What we discussed now. First, what Banach space we need to prove. Banach spaces, linear transformation, 4 conditions there based upon 4 conditions. One theorem we proved. Next, we discussed about non-Banach's theorem for real linear space. So one more corollary 2.4.2. So now clear the board. Corollary. So corollary, what is 2.4.2? Right. So let P of X be a sublinear. Let P of X be a sublinear functional. Sublinear functional. Sublinear functional. On a real linear space N. On a real linear space N, real linear space N, then there exists a linear functional. So corollary means theorem. Yeah. On a real linear space N. Okay. Real linear space N. Then there exists a linear functional. Then there exists a then there exists a linear functional F defined on N. Linear functional F defined on N such that minus of P of minus X less than or equal to F of X less than or equal to P of X, comma, X belongs to capital N. What is that? So corollary 2.4.2. What is that corollary? Corollary has a statement. So let P of X be a sublinear functional on a real linear space. Then there exists a linear functional of F defined on N such that minus P of minus X less than or equal to F of X. Less than or equal to, let's say, this part I will write once again because minus P of minus X less than or equal to F of X less than or equal to P of X, comma, X belongs to N. X belongs to N. What is N? N is a normal linear space. So corollary. So first clear the board and then we'll be proof of the corollary. Proof of corollary. Proof. What is it? Let X naught belongs to capital N. Right? X naught belongs to capital N. Define the linear subspace. Define the linear subspace. Define the linear subspace. Capital M. Capital M that equal to alpha x naught such that alpha is a scalar. Alpha is a scalar of n of capital N and a functional f naught and functional f naught. What is the given? That x naught belongs to n. X naught belongs to n. Define the linear subspace capital M that equal to alpha x naught. Alpha x naught. So alpha is a scalar. Scalar is nothing but real number of n, normal linear space, and functional f naught. And functional f naught. So on M as follows. On M, on capital M as follows. No? As follows. So f naught. Here f naught. F naught. F naught alpha x naught. Alpha x naught equal to alpha p of x. Is that alpha p of x? Then it is easy to see that. Then it is easy to see that. Then it is easy to see that f naught is a linear functional. F naught is a linear functional. F naught is a linear functional on M. On M. And f naught x less than or equal to p naught of x. On f naught x less than or equal to p of x. P of x. So x belongs to capital M. 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 Then by the above theorem, above theorem means main theorem. What is that above theorem? What we proved? Banach's theorem for a real linear space. That above theorem. Above theorem. There exists a linear extension. There exists a linear extension. Exists a linear extension. F of f naught. F of f naught. F of f naught. To the space n such that space n such that f of x less than or equal to p of x for all x belongs to capital N. This is the corollary proof. I will explain once again proof. So what is the first of our statement? Corollary 2.4.4. Let P of x be a sublinear functional on real linear space N. then there exists a linear functional f defined on n such that minus p of minus x less than or equal to f of x less than or equal to p of x comma x belongs to n. So this is corollary we need to prove using corollary is nothing but co-theorem of the main theorem. So let x naught belongs to capital N. Define the linear subspace M equal to alpha x naught comma alpha scalar of n and functional f naught on M as follows. As follows means f naught alpha x naught equal to alpha is the scalar now. That's why we need to take outside alpha of p of x. Then it is easy to see that f naught is a linear function on M on f naught x less than or equal to p of x. X belongs to M. Then by the above theorem, what is above theorem? Above theorem is the Hahn-Banach theorem in is real linear space. What is that statement? That p of x be a sublinear functional on real linear space n and M. A linear subspace of n and f naught a real valued linear functional defined on M. Let f naught satisfy f naught x is less than or equal to p of x on M. Then there exists a real valued linear functional f dash on n such that f dash is an extension of f naught and f dash x less than or equal to p of x on n. So here that is the so then it is easy to see that f naught is a linear function on M on f naught x less than or equal to p of x. F naught x is less than or equal to p of x, we proved above theorem. So x belongs to M. Then by the above theorem, there exists a linear extension of f naught to the space n such that f of x less than or equal to p of x for all x belongs to n. So have to clear the board. So next another theorem is this is also Hahn-Banach theorem for complex. Hahn-Banach theorem for complex. Banach theorem for complex number. Theorem number 2.4.3. Theorem 2.4.3. Hahn-Banach theorem for complex. Hahn-Banach. Banach theorem. Hahn-Banach theorem for complex linear spaces. For complex linear spaces. Complex linear spaces. So statement, what is that? Let P be a semi-norm. Let P be a semi-norm. Semi-norm defined on complex linear space. Defined on complex linear space. Linear space defined on complex linear space. Linear space N. Linear space N, capital N. Let M be the complex linear space subspace. Let M be the capital M be the complex linear subspace. Complex linear subspace. Complex linear subspace of N. And F a complex linear functional and FA, complex linear functional. Complex linear functional. Complex linear functional. Linear functional. Defined on M such that. 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 So mod f of x is less than or equal to p of x or on M on M on capital M on capital M. There exists a complex linear functional. There exists a complex linear functional. Linear functional. F dash defined on M. F dash defined on N. Defined on N. Such that F dash is the extension of F. F dash is the extension of F, and F dash x mod F dash x mod F dash x less than or equal to P of x for all x in N. For all x in N. So now clear the board. So next, proof. So we have a little time. Just probably try to finish the proof. Proof. What is the proof? Orally, I will explain it. So first we observe that a restriction of scalar multiplication to real numbers. The resulting linear space is a linear space if f of x equal to g of x plus I of h of x. This is nothing but complex number. G of x plus I of x is not a plus ib is there now. So connectivity a plus ib is nothing but g of x plus I of h of x is a complex number. So here g of x, here g of x, comma g of x and h of x. These two are real and imaginary parts of real and imaginary parts of f of x. So g of x is the real part and I h of x is the imaginary part. So g h are real linear function defined on M. Thus, mod g of x less than or equal to mod f of x. No? Mod g of x mod g of x is less than or equal to mod f of x, less than or equal to p of x, and h of x less than or equal to mod of f of x less than or equal to p of x for all x belongs to m. Since for each x belongs to m, so g of I of x plus I h I of x is f of ix that equal to I of f of x, I of g of x plus I of h of x that equal to minus h of x plus I g of x, where h of x equal to minus g of ix for x belongs to capital M. Similarly, so g is a real valued linear functional defined on M, such that g of x is less than or equal to p of x for all x belongs to capital M. Then by the above theorem, above theorem means Van-Banach theorem for real numbers. So hence g dash of x minus g of minus x less than or equal to p of minus x that equal to p of x. So that p of x and g dash of x less than or equal to p of x. Modulus of g dash of x is less than or equal to p of x. So for x belongs to capital N. So define f dash x. Define, clear before. Define here. Define f dash of x that equal to g dash of x minus I into g dash of ix. So then f dash x plus y equal to f dash x plus f dash y. So f dash I of x equal to g dash of I of x minus I of g dash of minus x equal to I g dash of x. That is the minus I square g dash of I of x that equal to I of g dash of x minus I dash g dash of ix that equal to I of f dash x. Hence f dash is a linear on n. Hence f dash is linear on n. We prove that f dash x is, we have to prove that f dash x. So mod f dash x less than or equal to p of x. So for all x in n. So let us write f dash x. Let us write f dash x equal to r e power I theta. E power I theta. So e power I theta for f of x is implies real value, complex valued. F of x is complex valued function. Then if mod of f of x e power minus I theta f dash x e power minus I theta x. So r is a positive real. Then it follows that f dash x equal to f dash e power I theta of x that equal to g dash of e power minus I theta x. Since f dash e power minus I theta is a positive real number, that is less than or equal to 1 g dash of e power minus I theta x. So less than or equal to p of e power minus I theta. So that equal to mod of p of x. So x belongs to n. So thus f dash x is f dash x less than or equal to p of x for all x belongs to n. Thus f modulus of f dash x equal to f dash e power minus I theta equal to, so f dash x is less than or equal to p of x for all x in capital N. This completes the This completes the proof of Banach theorem, proof of the theorem. So what we discussed. So what we discussed in this chapter, unit 2, Banach spaces. In Banach spaces, we discussed first linear. What we discussed linear transformations. That 4 properties. So 4 properties based upon we proved one theorem equivalent to equivalent theorem. Next, what we did on Banach's theorem. On Banach's theorem for real linear space. We proved. And what we proved next on Banach's theorem for complex valued function. We proved. We proved 3 theorems. So most important theorems. Okay, now clear. Clear. Let's stop sharing. Thank you. Thank you very much.